This process of converting decimal numbers to an arbitrary base b can also be represented in the form of an algorithm, which can be expressed in any language of choice. For example, here we have an algorithmic description of this process written as a procedure with the name base b expansion. So the idea is to be able to convert a number n, which is a decimal number, into base b, which is a positive integer. Base b is 2 for binary numbers, 10 for decimal, 8 for octal, and 16 for hexadecimal numbers. So we can provide this procedure or function, a number expressed in decimal, and a choice of the base. Now this algorithm starts with assigning the status of the first quotient to the number. Okay? So imagine this is the decimal number. So we say that in the first step, we say that this is q, and then we run a loop which keeps on going until this number changes to 0. Okay? This is where this loop breaks. And every time q changes its value to the new quotient of that step. So there are two things we compute in every step. One is the remainder, and another is the quotient. This is the step where we compute the quotient, and that represents the kth bit of the decimal number n in this case. For example, in the first step we get a sub 0, then we get a sub 1, a sub 2, and so on until the quotient becomes 0. Okay, and how do we get the quotient? We divide the previous quotient by this base, which in this case is 8, by the number b, and we remove the fractional part. So in other words, we compute the floor function. For example, if this is 192 point something, some fractional part, then we ignore the fractional part by finding the floor function, and we only record the integer part at every step. And we keep on going this and increment k at every step, just to ensure that these are recorded correctly in the corresponding array as the correct index address. And then once we have q equals 0, we stop the loop and we get the base b expansion of a number.